Welcome back everybody. Today I'm going to solve an IMO 2020 problem. The statement is a bit lengthy. Feel free to pause the video and read through it, but I'm going to explain it in mathematical sense right now. Okay, so we are given a mountain. This is the mountain that we have and this is the up direction. And the question is, okay, telling us, okay, I have n squared checkpoints here, n squared checkpoints for some n fixed larger than 1. And there are two cable car companies. Company A, I'm going to use color red for it, and company B, I'm going to use color B for it. And these companies basically try to link these checkpoints together. So this is, for example, company 1 trying to link it using a cable car. So these are basically cable cars here used to link these checkpoints together. So each link is a cable car. And this is a upward, this is always going to upward direction, right? So I just basically, because I have the direction specified here, I'm going to just forgo putting a direction on the edge I have here. And there is some basic rules that this statement is basically emphasizing, and that's the same as saying, okay, I don't have an edge here. If I have an edge between these two checkpoints, then I cannot have an edge between these checkpoints and any other checkpoints later. So the starting points of no two cars are the same. I might have the end point of one cable car being the starting point of some other one, but I cannot have two cable cars sharing the starting point. The same for the end points. No two cable cars share the same end points, right? So for example, I cannot have, let's say, this one here, because these two cable cars right now are sharing these checkpoints. Okay? Sounds good. And the question is basically defining two checkpoints being linked by company A, for example. If I can travel from checkpoint 1, the first one, to the next one, using only A-links, using only cars, cable cars from company A, right? So, for example, if I didn't have this cable car here, and let's say I had one from here to here, you can see that this checkpoint here is not linked with these checkpoints using cable cars from company A. But in the previous setup, these two were linked. Okay? And the same story for cable car B. And these two companies operates in parallel. So it's not like I have a cable car from company A here. That doesn't mean I can have the same cable car for company B. Company B. So this is B, and the red one is A, right? It's quite possible that two checkpoints are linked exactly for both companies. Okay. And the same rules that applies to company A's also applies to company B. So, for example, I cannot have this. I cannot have like something like this again, or if this, or I can't have this cable car here because there is a problem here, right? Okay, interesting. Now the question is asking us, what's the minimum number of cable cars to be used so that there exists two checkpoints somewhere here, so that both these checkpoints, such that these checkpoints are linked using both A cars and B cars. So basically saying, okay, I have this company and there is a car here and there is another A car here and then there is another A car here. So that basically means these two checkpoints are linked using company A cars, right? And the same for company B. The same for company B. That means these two checkpoints are fixed, right? And I managed to actually link them using company A's car, and I should be able also to link them using company B cars. So let's say I have, let's say this and this. So notice that the links don't have to be similar or anything like that, right? You just need to have a link. Once you have a B link, and then you have something like you have an A link like this for these two checkpoints, then you are good, right? So let's say I have these two checkpoints here. Let me use the existing ones. I have these two checkpoints, and I can like connect them using A. Let me use the color red for it, and I can also connect them using let's say. And then the question is basically asking us, okay, such a pair exists. Notice that, for example, in this example, these two pairs also satisfy the condition that we are looking for, right? And of course, if you have more and more cable cars, this would become more and more plausible, right? And so if you have very few cable cars, of course, the chances of this not happening is a lot. Like, let's say if I have only one cable car, then this is the K is the number of cable cars in the state. If I have only one cable car, then obviously that can happen. That is possible that there are no two checkpoints linkable with both A and B, right? So let's say I have these checkpoints here for n square of them, and I only have one cable car for each company. Let's say this is A, and let's say this is B, and that's it. So no two checkpoints are linked with both A and B cars. Okay, so we want to find the smallest value for K, so that this happens, right? So let's think about a counterexample. In situations like this, we basically need to say, okay, K is at least, we need to say, okay, K is at least like some function based on n, and then we need to find a counterexample for f of n minus 1, and then we need to show that if K is at least f of n, then we are good. That means this condition is satisfied, guaranteed, and then problem is solved, right? So in this problem, the claim is that K is at least n squared minus n plus 1. And so next I'm going to try to prove it. So the proof has two steps, right? The proof has two steps. Step 1 is that find a counterexample using K equal to n minus 1, K equal to n squared minus n, sorry, using K equal to n squared minus n. Then step 2 is prove the statement, prove this statement using when let's say when K is n squared minus n plus 1. Of course, if you have more cable cars, then the better, right? But the smallest value is n squared minus n plus 1. Okay, so let's do the first step first. The first step is, the idea of it is as follows. How can I actually make a counterexample? How can I actually configure these cable cars in such a way that no two checkpoints are connected using A links and B links simultaneously, right? So the idea of it is as follows. Suppose that I divide these checkpoints into n clusters. Okay, this is direction. I just rather not to write it, but assume that this is direction, and these are the clusters I have. And I'm not saying anything about the number of these clusters. These are just the groups that I have for the checkpoints. And I'm going to do this. I'm going to say, okay, only links stuff within these cluster. Okay, only let me write it down here. Only use let's say A links checkpoints within a cluster, within clusters only. Within clusters only. Right. And let's also say that B links checkpoints inter-clusters only. Let's say between clusters only. Between clusters only. Okay? And this is the idea for actually constructing the counterexample. So in this setup that I have here, I want A to only link checkpoint within a cluster, right? Within a cluster, and in that way, the links looks like this. This is the max I would get. I just link everything with the next one. And B links checkpoints between clusters only. So it's quite the opposite. So that means I'm gonna link this with this, link this with this, link this with this, link this with this, and then the next one with the next one here, and go on, right? This one, then this one, then this one. You get the idea, right? And this way, no two checkpoints are linked using both A and B. Because if for any two checkpoints, if they are inside the cluster, then they are linked only using A. And if they are outside of, if they are like in two different clusters, then they are linked using only B cable cars. Okay, awesome. Now I just need to find the number of cable cars I get here. Notice that in this statement, both A and B have the same number of cable cars, right? And so here, I just let me just compute the number of cable cars. For each cluster here, let's say for here, I have n. Okay, I didn't actually say anything about the number of clusters or the size of them. I have n squared checkpoints, right? Let's say divide them into n clusters. Each cluster n checkpoints each. Sounds good? Seems like a very natural idea, right? I mean, we have n squared, divide them by n. Each of them the same amount. And so now the number of cable cars I get here is that n minus 1 for each, for red, within inside one cluster, and there are n clusters, so this would be for red. And I need to check that I would get the same amount for B as well, right? And so for B is, what happens is like, for the first, just track the first checkpoints. It's a pass of n minus 1, length of n minus 1, and there are n of these passes, right? I have one starting with the first one, and then another one starting with the second one, and so on. So I would again get like the same amount, n times n minus 1 for cable cars B as well. And that's basically a step 1 done, right? I provided the counterexample using n squared minus n cable cars, and next I need to show that if I just add one single more cable car to the entire story, then I would find the 2 checkpoints I'm looking for. Okay, let's say for example, in this example, let's say I have like this one and this one, right? Then what would happen is that these two are connected using A, and they are also connected using B, right? And let's say I add something else. Let's say I add this one with this one. Then again, these two checkpoints are connected. For why? Because let's say I have a something like this here, and then what I would get is that this checkpoint and these checkpoints are connected using the blue or company A, and they're also connected using company B. But this was just for this counterexample, right? I don't need to actually prove it, because I'm going to prove it in the most general case, which is a step 2, right? Okay, now we want to show the second step, namely that k equal to n squared minus n plus 1 cable car is enough to have the desired checkpoints pair, right? So the idea lies in a very fundamental definition in combinatorics or graph theory in general, and that's the idea of largest path. So for each cable car that we have, just construct the longest path you can go using the cable cars that you have, starting from this checkpoint, right? And I would call this a largest path if I cannot add anything more to it. That means such a thing doesn't exist and such a thing doesn't exist. So I cannot make this path any larger, right? And because of the assumption that so this was the assumption that we had. No two cable car share the same start or nor end. Then because of this assumption, these largest paths are completely disjoint. That means they do not share any edge or any even vertex. They do not share any checkpoint. Why is that, right? Suppose that I have this largest path here, and suppose there is another largest path sharing a checkpoint with, let's say, this checkpoint, right? Then what would happen? I have this checkpoint, and if the largest path is not exactly the one that I have, let's say there must be an edge somewhere like this. And that's a contradiction. Because the only way I could immediately arrive at this checkpoint is using this cable car I have. So I cannot have any other one. Right? So these largest paths are all disjoint. And how many and this would help me to determine the number of largest paths I have. How many cars I had? How many edges cable car? Exactly k, right? Each of them have a unique endpoint, which is not shared with other ones based on this assumption. So I have n squared minus k, which is n minus 1 checkpoints that are not like endpoints that are not basically endpoints of any cable car, right? Of any car. Correct? This was very straightforward. So each cable car has a unique endpoint. There are k of them. And there are n squared checkpoints. So there are n squared minus k checkpoints, which are not the endpoint of any A cable car. Okay? And each of these n minus 1 checkpoints are basically the starting point of a unique large space, right? So notice that I'm not claiming that you can connect two checkpoints using A cars. That means like because I'm saying that okay, these n minus 1 checkpoints are not endpoints of any A car. That doesn't mean like I can connect this one, for example, with some other checkpoints using A cars. That basically means this checkpoint is not the endpoint of any A car. And if you construct a largest pass, you will notice that the starting point must be one of these n minus 1 checkpoints. It must be, right? Because if it's not, then you have an edge here, you have a cable car here, and that basically make this pass larger. So the starting point cannot be one of the endpoints. So the starting point of any largest pass is one of these n minus 1 checkpoints. And if there is no cable car here connecting this checkpoint to any other one, this checkpoint standalone will be a largest pass, right? And this is actually telling us the number of largest pass is equal to n minus 1, because for any of these n minus 1 checkpoints that are not the endpoint of any A cable car, you just initiate or start the largest pass, and that would be unique largest pass associated with that checkpoint. And largest pass for this joint, and that's it. That's actually a proof that number of largest pass is exactly n minus 1. Again, I emphasize that a standalone checkpoint itself could be a largest pass. Okay, now here, now I'm gonna consider a mapping that would basically map each checkpoint to a pair of largest pass using A car and a largest pass using B cars, right? Basically because each checkpoint must lie inside exactly one, not at least exactly one largest pass using A cars, and also a unique largest pass using B cars. Now here notice that I have n squared checkpoints, and I have n minus 1 squared pair of largest pass using A cars and largest pass using B cars. So there are two checkpoints mapping to the same pair. So let's say I have this checkpoint and I have this checkpoint, and they basically belong to the same largest pass using cable cars A, and they also belong to the same largest pass using cable cars B. And these two checkpoints basically are the answer to the questions. So basically I proved that there are two checkpoints belonging to the same largest pass using A cars and the same largest pass using B cars, and because the number of checkpoints is n squared and the number of largest pass using A cars is n minus 1, the number of largest pass using B cars is also n minus 1, so I have at most n minus 1 pair of largest pass using A cars and largest pass using B cars. And so two checkpoints here must have the same pair. Let's say this one is LA and this one is LB, and that basically completes the proof.